Alright, so this is just a quick little video explaining how the RSA encryption works and the mathematics behind it using just a little bit of basic number theory. Alright, so let's get started. So first, to start off, I want to give a quick overview of how the algorithm works. So suppose you have two people, Bob and Alice. Right? And Alice wants to send a message to Bob securely. What Bob does is he'll generate two prime numbers, P and Q, and these will be traditionally very, very large, so something like 100 digits or so. And another integer, E, such that E divides P minus 1 and Q minus 1, plus 1. Alright, seems a bit random, but this is what makes it work. So, what he'll do with these numbers now is take the product P and Q and his integer E, and Alice will take these two numbers. So this is broadcasted to the world and basically pretty much anyone who wants to send a message, right? So Alice will take these two numbers and she'll take a message M and raise it to the power of this number E, take it congruent modulo PQ. That will give her a coded message which she can send securely to Bob, and Bob can receive this C, this coded message, right? So it comes over here, C. Now the magic part which makes this whole system work is that the decryption key for this D, right? So some key D, which if we take mod PQ will give us back our M, is linked to these two numbers. So now we'll show how we can get this value D. Alright, so take all this out. So to summarize, we have two prime numbers P and Q, some integer E such that E divides P minus 1, Q minus 1, plus 1. Alright, and the function that we're going to be using to encrypt and decrypt the messages takes this form. If we take M, raise it to E, congruent PQ gives you the cipher, and other way around, PQ gives you back the message, right? And you see, from these two cases, we also get another relation that we hope to be true if this were to work, right? That if you encrypted the message and then decrypted again, you'd hope to get back M. Now, we just leave these up here for the moment. We'll introduce a theorem called Fermat's little theorem. Which states that given some integer A raised to the power of P minus 1, that will be congruent mod P to 1. Alright, given that P is a prime number, so I'll write this down. P is prime, and A and P are co-prime. So we get GCD AP equals 1. Right? So now using this, we can write it up here. AP minus 1 mod P equals 1. But this works for any prime number, so I can make another equally valid statement. Say AQ minus 1 mod P equals 1. Alright? And we have a property of modular arithmetic that if you take any one of these and you raise both sides to the same exponent, the relation will still hold. So what I'm going to do is raise this 2 by Q minus 1, and I'll raise these two by P minus 1. So we get, so let's say 1, 2, that becomes a P minus 1 q minus 1 mod p 1, and it's 1, so it's raised to anything, just stays 1. And 2 becomes a q minus 1 p minus 1. That was, oops, sorry, made a mistake here. That should be q, and that will be q1. Alright, so now notice that what we have here is a system of congruences where the different modulos are co-prime. So what we can do here is use the Chinese remainder theorem to give us a new statement, namely this one, p minus 1, q minus 1, congruent pq to 1. And we're getting pretty close to the form that we want. So what we do now is, what we'll do here now is we'll take this expression and times it by a, which will give us a p minus 1, q minus 1, plus 1, pq, a. Right, and notice this is very similar to what we have here. So it's the same structure. So what we can do is just set a to equal m, and we'll set the exponents to equal. Pd equals p minus 1, q minus 1, plus 1. And notice that we've chosen our e in such a way that it divides p minus 1, q minus 1 plus 1. And this is just another way of writing that statement. So this shows that given that we've chosen our e correctly, we will get precisely these functions working. So now if we clear this up a bit, so we'll leave these two, and I'll bring it over here. Q minus 1 plus 1, PQ, A. And we have PD. So, to summarize how this then fits together, remember we had our encryption function is this one here, and given if we receive a ciphered message, we can decrypt it using this. Now we have an explicit expression for the key D. So we get from this one, D equals P minus 1, Q minus 1, plus 1 over E. And so we have this here, and let's just remember that, so say Bob, he'll have private keys he keeps to himself, the number P, Q, and D, right? And he'll broadcast to everyone the product PQ and E, right, that, E. So anyone can use P, Q, and E to encrypt messages to send to him, to be decrypted only by him, because he knows D, right? And he can only know D. D is very easy to compute if you know P and Q, right? Because we have this one here. If we only knew PQ, we'd have to factorize PQ first into P and Q. But this is a famously difficult problem. And with the digits, with the scale of digits that we use for P and Q, up to 100 or whatever it is, I'm not too sure, it will take the fastest supercomputers in the world, something like 200, 300 years to even factorize one number. But then even if that happens, you can easily just generate another two numbers, and that would just make that whole cracking process completely pointless. And so you have it.